Right now, in the single second it takes you to read this sentence, the sun has destroyed 4 million tons of itself. It has taken that mass, an amount roughly equal to a small mountain, and converted it completely into light and heat, flinging it outward across the solar system at the speed of light, a tiny fraction of it falling onto your skin at this very moment. It has been doing this every second for 4.5 billion years. In that span, it has annihilated a quantity of its own substance, greater than the mass of every planet, every moon, every comet, and every grain of asteroid dust in the solar system combined. And it has barely noticed. The sun is so enormous that you could pour 1,300,000 Earths inside it and still have room left over. It holds more than 99.8% of all the matter in our entire solar system inside its single glowing body. Yet every second of that magnificent burning is also a second of dying. The death of the sun is not a distant fantasy. It is not a poetic abstraction invented to frighten children. It is a certainty, already written, already in progress, encoded in the very same physics that allows the sun to shine at all. Here is what will shatter everything you think you know about the star that gives us life. The sun is not a fire. It will not simply burn down to embers and go out, and the way it actually dies is far stranger, far slower, and far more beautiful than anything you were ever taught in a classroom. Most people imagine the sun's death as a single moment, a flicker, and then darkness. The truth is a transformation that unfolds across billions of years, passes through forms that have no name in ordinary language, and ends with our star becoming something so dense, so quiet, and so patient that it will outlast almost everything else in the cosmos. If you enjoy slow, calm journeys through the deepest truths of the universe, do me a small favor and hit that like button and subscribe. It genuinely helps this channel grow and lets me keep making these deep dives for you. So settle in, make yourself warm and comfortable, let the world outside go quiet, and let your only task for the next while be to follow this one question wherever it leads. Let's begin. For almost the entire history of our species, no one had any idea what the sun actually was. They knew it was warm. They knew it was bright. They knew that when it vanished below the horizon, the world grew cold and dark, and that when it returned, the world grew warm and alive again. That was the whole of human knowledge about the most important object in the sky for tens of thousands of years. People built temples to it. They tracked its movements with standing stones. They told stories in which it was a god in a chariot, or a wheel of fire, or the open eye of something vast and watchful. But not one of them could have told you what the sun was made of, or how it produced its heat, or how long it had been shining, or how long it would continue. The honest answer, for most of human history, was that nobody knew. The first people to ask the question scientifically ran almost immediately into a wall. By the 1800s, physics had advanced enough that scientists could attempt a simple calculation. They asked a reasonable question. What if the sun were made of the best fuel we knew, of pure burning coal? How long would it last? The answer was devastating in a way nobody expected. If the sun were a solid ball of coal the size we knew it to be, burning as fiercely as it burns, it would consume itself completely in only a few thousand years. Not billions, not millions, a few thousand. And we already knew, from the rocks and the fossils and the slow grinding of rivers carving canyons, that the Earth was vastly older than that. Something was profoundly wrong with the picture. The sun could not be a fire, because no fire could possibly last long enough. This is the first great clue to the mystery of how the sun dies, and it arrived disguised as a problem about how the sun lives. In the 1850s and 1860s, two of the finest minds of their age turned to the puzzle. In Germany, the physician and physicist Hermann von Helmholtz proposed an idea. In Scotland, the physicist William Thomson, who would later be known to the world as Lord Kelvin, developed it further. Their idea was elegant. Perhaps the sun was not burning at all. Perhaps it was simply falling. A vast ball of gas, pulled inward by its own immense gravity, would compress. and compression generates heat. Anyone who has ever felt the warmth of a bicycle pump after inflating a tire has felt a tiny echo of this effect. If the sun were slowly shrinking under its own weight, the heat from that contraction could explain its glow. It was a brilliant idea, built on solid physics. And it gave an answer to the great question: how old is the sun? Their calculation said the sun could be perhaps 20 million years old. Possibly a little more, possibly a little less. There was only one difficulty, and it was enormous. 20 million years was nowhere near enough. The scientists, studying the layers of sediment laid down over unimaginable ages, insisted the Earth was far older than 20 million years. And in 1859, Charles Darwin had published a book proposing that all the living things on Earth had arisen through a process of slow change over countless generations. A process that would require not millions of years but hundreds of millions, perhaps far more. The physicists and the geologists were at war, and the sun was the battlefield. Kelvin was one of the most respected scientists alive, and his physics seemed unimpeachable. Yet the rocks told a different story. Someone was wrong, and nobody could say who. The resolution would not come from better measurement. It would come from the discovery of an entirely new kind of energy that no one in Kelvin's generation had ever imagined. That door opened in 1896 in Paris, almost by accident. A French physicist named Henri Becquerel left some uranium salts resting on a photographic plate wrapped in black paper in a drawer, expecting nothing. When he developed the plate, he found it fogged, as though it had been exposed to light, even though no light could possibly have reached it through the paper. Something invisible was streaming out of the uranium itself, carrying energy, with no apparent source and no apparent end. In the years that followed, Marie and Pierre Curie in that same city pulled apart this mystery and gave it a name: radioactivity. Here was matter that poured out energy continuously, for years, for centuries, seemingly from nothing. The old rule that you could only get energy out by burning something, or by letting something fall, had just been broken. There was a reservoir of energy hidden inside matter itself, locked away where no one had thought to look. The key that fit this lock was forged in 1905 by a 26-year-old patent clerk working in an office in Bern, Switzerland. His name was Albert Einstein, and in a single short paper, almost as an afterthought to a larger work, he wrote down a relationship that would reorganize our understanding of reality. Mass and energy, he showed, were not two separate things. They were the same thing in two different forms, and you could convert one into the other. The exchange rate was set by the speed of light multiplied by itself, an almost incomprehensibly large number. This meant that even a tiny amount of mass, if it could somehow be converted into energy, would release a staggering quantity of power. A paperclip's worth of matter, fully converted, could supply a small town with electricity for years. Suddenly the impossible problem of the sun looked different. The sun did not need to find enough fuel to burn for billions of years. It needed only to convert a tiny fraction of its own colossal mass into energy, and the numbers would work. But knowing that mass could become energy did not yet explain how the sun did it. For that, scientists needed to know two more things. They needed to know what the sun was actually made of, and they needed to understand the precise process that turned its substance into light. The first of those answers came in 1925 from a young woman at the Harvard College Observatory, whose name deserves to be far more famous than it is. Cecilia Payne, a British astronomer working in the United States, was studying the light of stars, analyzing the dark lines that appear when starlight is spread into a rainbow. Those lines are fingerprints. Each element, when it is hot, absorbs light at specific colors, and by reading those missing colors you can read the chemical composition of a star from across the void. For her doctoral thesis, Payne did this with extraordinary care, and she arrived at a conclusion so shocking that she very nearly was not allowed to publish it. The prevailing belief at the time was that the sun and stars were made of more or less the same stuff as the Earth: iron, silicon, oxygen, the familiar materials beneath our feet. Cecilia Payne's analysis said something completely different. The stars she found were overwhelmingly made of the two lightest elements in existence, hydrogen and helium, not slightly more hydrogen than the Earth has. Astonishingly, almost unbelievably more. The Sun was a vast sphere of hydrogen, with helium making up most of the rest, and everything else, all the iron and oxygen and carbon, amounting to only a thin seasoning of the whole. This conclusion was so far outside accepted wisdom that a senior astronomer reviewing her work persuaded her to add a line saying that the result was almost certainly not real. She did, and then, a few years later, that same astronomer ran the numbers himself, found that she had been right all along, and the truth could no longer be denied. The Sun was made of hydrogen. The fuel had been identified. Now the final piece could be assembled, and here the story becomes genuinely strange, because by the rules of ordinary physics, the Sun should not be able to do what it does at all. The Sun's core is hot, ferociously hot, around 15 million degrees. But it is, oddly, not quite hot enough. To force two hydrogen nuclei to fuse together, you have to push them close enough to touch, and hydrogen nuclei are positively charged, so they repel each other fiercely, more fiercely the closer they get. At 15 million degrees, the particles in the Sun's core are moving fast. But by the strict accounting of classical physics, almost none of them are moving fast enough to overcome that repulsion and fuse. By those rules, the Sun should barely shine at all. The resolution came in 1928 from a physicist named George Gamow, who applied the bizarre new science of quantum mechanics to the problem. In the quantum world, particles do not have exact positions. They are smeared out into clouds of probability, and this means that a particle can sometimes appear on the far side of a barrier it did not have enough energy to climb over, as though it had tunneled straight through a mountain. This effect, called quantum tunneling, is rare for any single pair of nuclei, but the Sun's core contains a number of particles so vast it dwarfs comprehension, and rare events, multiplied across an unimaginable number of chances, happen constantly. The Sun shines not because its core is hot enough, but because the laws of the quantum world allow what the laws of everyday experience forbid. The last great name in this chain belongs to a physicist named Hans Bethe, who in 1939, working at Cornell University in New York, finally wrote down the detailed step-by-step process by which the Sun turns hydrogen into helium and light. He traced the exact sequence of nuclear reactions, the chain of collisions and transformations that begins with 4 hydrogen nuclei and ends with a single helium nucleus, plus a flash of energy. And here is the crucial detail, the detail that explains everything that will follow about the death of the Sun. When 4 hydrogen nuclei combine to form 1 helium nucleus, the helium nucleus weighs very slightly less than the 4 hydrogen nuclei that made it. That missing mass, less than 1% of the total, has not vanished. It has become energy, exactly as Einstein predicted. The Sun shines by very slowly converting itself into a lighter element and pouring the difference out as light. For this work, decades later, Hans Bethe would receive the Nobel Prize. So now, at last, we can answer the question that defeated humanity for tens of thousands of years. The Sun is a vast sphere of hydrogen, held together by its own gravity, with a core squeezed so hard and heated so high that hydrogen nuclei fuse into helium, releasing the energy stored in the tiny difference in their mass. That energy works its way to the surface and escapes as the sunlight that warms your face and feeds every living thing on Earth. The Sun is not burning, it is transmuting. And this brings us to the truth that everything else in this story rests upon. The truth that turns a question about how the Sun lives into a question about how the Sun dies. A star is not a permanent object. A star is a process. It is a slow, controlled, self-consuming reaction, and the very thing that makes it shine, the conversion of its own substance into light, is also the thing that is using it up. Every photon of sunlight that has ever fallen on Earth was paid for with a small piece of the sun's body that no longer exists. The brighter a star burns, the faster it spends itself. The sun's death is not an event waiting somewhere in the far future. It began the moment the sun first ignited, and it has been happening, second by second, mountain of mass by mountain of mass, ever since. We are not waiting for the sun to start dying. We are watching it die right now, very slowly, in the gentlest light we have ever known. To understand how the sun will die, you must first understand the single most important fact about how it stays alive. A fact so simple to state and so profound in its consequences that everything else in the life and death of every star descends from it. A star is a war. It is a war between two opposing forces, fought in perfect balance, in the same place, at the same time, for billions of years. On one side is gravity. Gravity is relentless. Gravity wants to take the entire vast mass of the sun and crush it down toward a single point at the center. Gravity never rests, never weakens, never changes its mind. It pulls every gram of the sun's substance inward, always, with a patience that is total. If gravity were the only force at work, the sun would collapse in on itself in a matter of minutes, falling inward at tremendous speed until it was crushed into something almost unimaginably small. The only reason this does not happen, the only reason the sun has a size at all, is that something pushes back, that something is pressure. At the core of the sun, the fusion of hydrogen into helium releases a continuous torrent of energy. And that energy creates an outward push, a pressure that holds the crushing weight of gravity at bay. The hot gas wants to expand, gravity wants to contract. And across the whole body of the sun, layer by layer, these two forces settle into an exact standoff. At every depth inside the star, the outward pressure precisely balances the inward weight of all the material above it. This balance has a name. Astronomers call it hydrostatic equilibrium, and while the words sound technical, the idea is something you already understand in your body. It is the same balance that holds up a building. The walls push up exactly as hard as the weight of the floors above pushes down, and the building neither collapses nor flies apart. The sun is a structure of unimaginable size, holding itself up against its own catastrophic weight, using nothing but the pressure of the energy released by destroying itself. It is a building made of light and gravity, and it has stood, perfectly balanced, for longer than the Earth has had oceans. This distinction matters enormously, because it reveals why the sun is not, and could never be, a fire. A fire is a chemical reaction. It rearranges the bonds between atoms, and it is a clumsy, wasteful, low-energy affair. The sun does something different in kind, not merely in degree. It reaches inside the atomic nucleus itself, the dense knot at the heart of every atom, and it rearranges that, releasing the energy that binds the nucleus together. The energy locked inside the nucleus is millions of times greater than the energy locked in chemical bonds. This is why a fire made of the sun's material would last only a few thousand years, while the sun itself can shine for 10 billion. The difference is not that the sun is a bigger fire. The difference is that the sun is not a fire at all. It is a controlled nuclear reaction, the same kind of reaction that powers a hydrogen bomb, except that in the sun this reaction has been tamed, slowed, and held in a steady simmer by the weight of the star pressing down upon it. And this is where the true elegance of a star reveals itself, in a feature so clever it almost seems designed, though it emerges entirely from blind physics. The sun is self-regulating. It is its own thermostat, and it corrects its own mistakes without anything watching over it. Imagine the fusion in the core stumbling for a moment and burning too fast. The surge of energy swells the core outward, and a gas that expands is a gas that cools, and a cooler core fuses more gently, until the fire eases itself back down to where it began. The opposite stumble corrects itself just as quietly. Let the fusion falter and fade, and gravity presses inward, and a gas that is squeezed grows hotter, and the hotter core burns faster, filling the missing energy back in. Every error erases itself. Every disturbance is answered by its own opposite. The sun does not hold its balance through luck, or through some fragile coincidence that might one day fail. It holds it because the balance is woven into the physics itself, written so deeply into the relationship between heat and pressure and gravity that the star simply cannot run away with itself. It cannot suddenly flare into an explosion. It cannot abruptly gutter out into darkness. Push it, and it pushes back. Cool it, and it warms. This is why the sun has been so steady, so reliable, so unwavering across the entire history of life on Earth, holding its light within a narrow band for billions of years, while oceans formed and continents drifted, and the first living things crawled out of the sea. It is not a coincidence. It is the deepest property of what a star is. To appreciate how extraordinary this stability truly is, consider the journey a single particle of light takes to escape the sun. The energy created by fusion in the core does not simply fly out into space. The interior of the sun is so dense and so opaque that a packet of energy created at the center cannot travel in a straight line for more than a tiny fraction of an inch before it slams into a particle, is absorbed, and is then released again in a random direction. It staggers outward like a person lost in a vast crowd, taking a single step before being jostled in a new direction, over and over, billions upon billions of times. The result is almost impossible to believe. A single packet of energy created in the sun's core can take tens of thousands of years, by some estimates well over 100,000 years, to fight its way to the surface and finally escape as sunlight. The light that warms your face today was created in the sun's core before the last ice age ended, before the first cities were built, before agriculture, before written language. It has spent longer trying to leave the sun than our entire civilization has existed. Then, once it reaches the surface, it crosses the 93 million miles to Earth in only 8 minutes. Now we can begin to see the shape of the sun's interior, and within that shape, the first hidden seed of its death. At the very center lies the core, a region extending out to perhaps a quarter of the way to the surface, but containing a large fraction of the sun's total mass, squeezed to a density many times that of solid lead, yet behaving as a gas because of the ferocious heat. This is the only place fusion occurs. Surrounding the core is a vast zone where energy travels by that slow staggering process, radiation passing from particle to particle. And in the outer layers, the energy is finally carried by enormous churning currents of hot gas rising and cooling gas sinking. A roiling motion like water boiling in a pot, but on a scale where a single rising column of gas can be larger than the entire Earth. At the surface, this boiling gives the sun its mottled, granular texture, and it is from this surface that the light at last breaks free. Every part of this structure exists in that same perfect balance, gravity pulling in, pressure pushing out, the whole gigantic machine holding itself in trembling equilibrium. Here is the problem. Here is the quiet catastrophe hidden inside this beautiful balance, the thing that guarantees the sun cannot live forever, no matter how stable it appears. Every second, the core fuses hydrogen into helium, and the helium does not leave. It is the ash of the nuclear fire, and it sinks and accumulates at the very center of the core, because it is heavier than the hydrogen around it. Helium does not fuse at the temperatures found in the sun's core today. It just sits there, building up, a growing sphere of inert ash at the heart of the star. With every passing second, the core contains a little more helium and a little less hydrogen. The fuel is being used up, and the spent ash is piling higher. This is not a sudden process. It is agonizingly slow, but it is utterly relentless, and it cannot be stopped or reversed, because it is simply the consequence of the sun doing the one thing that keeps it shining. The sun is dying of the very success of its own life. The more brilliantly and steadily it shines, the more helium ash it accumulates, and the closer it creeps toward the day when the hydrogen at its center finally runs out. But the death of the sun is not a simple matter of running out of fuel and going dark, and this is the point at which almost everyone's intuition goes wrong. You might imagine that as the hydrogen in the core is depleted, the sun would slowly grow dimmer, fading gently toward darkness like a lamp running low on oil. The reality is precisely the opposite, and it is one of the most counterintuitive facts in all of astronomy. As the sun ages and its core fills with helium, the sun does not grow dimmer. It grows brighter. Steadily, inexorably, decade by decade and eon by eon, the sun is getting hotter and more luminous. It is brighter today than it was when the dinosaurs walked the earth. It is far brighter today than it was when the first living cells appeared in the ancient oceans. The reason for this lies in the nature of that accumulating helium ash, and understanding it requires looking closely at what happens in the core as the hydrogen slowly disappears. Consider what the growing core of helium actually does. As helium piles up at the center, it adds mass to the core without contributing any energy, because it is not fusing. The core therefore grows heavier. A heavier core means stronger gravity at the center, which means the core must squeeze itself tighter and hotter to generate enough pressure to hold up the increasing weight above it. The remaining hydrogen, now sitting in a hotter, denser, more compressed core, fuses faster and more energetically than before. The strange result is that an aging star choking on its own ash burns its remaining fuel more furiously, not less. The thermostat that keeps the sun stable on short timescales cannot prevent this slow drift, because the very accumulation of helium changes the conditions under which the thermostat operates. The sun's brightness is not constant across its life. It is a rising curve, climbing ever upward, and that rising curve is the hidden clock counting down not to the sun's death, but to the death of every living thing that depends on it, an event that will arrive billions of years before the sun itself reaches its end. These calculations reveal a profound truth that the physics of stars encodes but everyday experience obscures. We tend to think of the sun as a fixed and changeless thing, the one reliable feature of existence, rising every morning exactly as it always has. On the timescale of a human life, or even of all human history, this is true. The sun your distant ancestors saw was for all practical purposes identical to the one you see today. But on the timescale of the Earth, on the timescale of life itself, the sun is a slowly changing star, growing hotter and brighter with a patience measured in hundreds of millions of years. And that slow change is the most important fact about our future as a species and as a world. The peaceful, life-giving sun is not our permanent companion. It is a star passing through the long, stable middle phase of its existence, and that phase, like all phases, will end. The balance that holds it steady is real, and it has lasted an almost unimaginable span. But it is a balance that is slowly tilting, and when it finally breaks, it will not break gently. To understand what this slowly rising brightness means for the future of our world, we have to begin with a strange puzzle from the deep past. A puzzle that took astronomers decades to even recognize, and longer still to accept. In 1972, two scientists, Carl Sagan and George Mullen, published a paper pointing out something that should not have been possible. When they calculated how bright the sun must have been billions of years ago, in the era when life was first appearing on Earth, they found that the young sun was far dimmer than it is today, perhaps only 70% as luminous. A sun that faint, shining on an Earth like ours, should have left the entire planet frozen solid. The oceans should have been sheets of ice from pole to pole, and yet the geological record is absolutely clear. There was liquid water on the early Earth. There were rivers and seas. There was life, thriving in those warm ancient waters, at a time when the sun was far too weak to keep the planet from freezing. This contradiction became known as the faint young sun paradox, and while scientists still debate exactly how the early Earth stayed warm, probably through a thicker blanket of heat-trapping gases in its atmosphere, the underlying fact is not in dispute. The sun was much dimmer in the past, and it has been growing steadily brighter ever since. This is the crucial reframing, and it changes everything about how we should think of our future. The danger to life on Earth is not the distant death of the sun. The danger is the sun's life, its long, slow, relentless brightening, which will become lethal long before the sun shows any dramatic sign of ending. We are accustomed to thinking that we have billions of years before we need to worry about the sun. In a narrow sense, this is true. The sun will not become a red giant for roughly 5 billion years, but the Earth will become uninhabitable for complex life far sooner than that. Not because the sun changes suddenly, but because it keeps doing exactly what it is doing now, growing imperceptibly hotter, century after century, until the slow accumulation of heat tips our world past a point of no return. The sun does not have to die to kill us. It only has to keep living. The first crisis arrives not with fire, but with suffocation, and it strikes at the very foundation of life on land. To understand it, you have to know about a slow geological process that has been quietly governing the Earth's climate for billions of years. Carbon dioxide in the atmosphere is gradually removed by the weathering of rocks, a chemical process in which rain and rock combine to pull carbon dioxide out of the air and lock it away in stone. This process speeds up as the planet gets warmer. So as the sun brightens and the Earth heats, the weathering accelerates, stripping carbon dioxide out of the atmosphere faster and faster. For us, in our era, carbon dioxide is something we have too much of. But across the long arc of the future, the opposite problem looms. The level of carbon dioxide in the air will fall, slowly, inexorably, dragged down by the warming the sun imposes. And carbon dioxide is not merely a heat-trapping gas. It is the raw material of life itself. Plants breathe it in and use the energy of sunlight to build their bodies from it. This is photosynthesis, the process that feeds nearly every living thing on the planet, directly or indirectly. Without carbon dioxide, plants cannot grow, and without plants, almost nothing else can survive. Consider what this means. In perhaps 500 to 600 million years from now, by current estimates, the level of carbon dioxide in the atmosphere may fall so low that the most common form of photosynthesis can no longer function. The great forests, the grasslands, the crops, the vast green machinery that has covered the continents and filled the air with oxygen for hundreds of millions of years would begin to fail. Some specialized plants, using a more efficient method of capturing carbon dioxide, might hold on a while longer, but eventually, as the brightening sun continues to drive the carbon dioxide down, even they would reach their limit. The land would grow barren. The oxygen that these plants pour into the atmosphere, the oxygen that animals breathe, would no longer be replenished, and over time it too would dwindle. The death of the plants would be the death of the animals. The rich, complex, breathing world of forests and creatures that we know would quietly disappear, not in a catastrophe, but in a slow fading, a starvation at the base of the food chain that climbs upward until nothing complex remains. And all of this could happen while the sun still looks, to any casual glance, exactly as it does today. This is the unsettling reality of deep time. The processes that will end the living world are already in motion, turning so slowly that across all of recorded history they have not moved enough to notice, yet turning with an absolute certainty that no power can halt. But the failure of photosynthesis, devastating as it would be, is only the first act. The second act is hotter, and far more violent in its consequences, and it strikes at the one thing that has defined our planet from almost its very beginning: the oceans. For more than 4 billion years, the Earth has had liquid water on its surface, vast and deep and continuous. This is, as far as we know, the single most important fact about our planet, the feature that makes it a living world rather than a sterile rock, and the brightening sun is going to take it away. As the sun grows hotter, more and more of its energy falls on the Earth, and the planet's average temperature climbs. At first the effect is gradual, a warming that the Earth's systems can partly absorb, but there is a threshold, a tipping point, beyond which the warming becomes self-reinforcing and unstoppable. The mechanism is one of the most important and most frightening processes in planetary science. As the surface warms, more water evaporates from the oceans into the atmosphere. Water vapor is itself a powerful heat-trapping gas. More water vapor in the air means more heat is trapped, which means more warming, which means even more evaporation. This is a feedback loop, a cycle that feeds on itself and accelerates. Scientists call the early stage of this the moist greenhouse, and its later, runaway stage the runaway greenhouse. Once the sun becomes bright enough to push the Earth past this threshold, the process takes on a terrible momentum of its own. Consider what this means for the world we know. As the runaway greenhouse takes hold, the oceans do not simply shrink, they boil. The water rises into the atmosphere as vapor, thickening the air into a dense, scalding, suffocating shroud. High in this superheated atmosphere, the water molecules are broken apart by sunlight into their component atoms. And the lightest of those atoms, hydrogen, escapes into space, lost forever. The Earth bleeds its oceans away into the void, molecule by molecule, until the seas that cradled the origin of life run dry. The surface temperature would climb past the boiling point of water and keep climbing, hundreds of degrees, until the rocks themselves grew soft. By current estimates, this catastrophe will arrive in roughly 1 billion years, possibly a little sooner, possibly a little later, depending on details of the Earth's atmosphere that are difficult to predict across such immense spans of time. But the direction is not in doubt. The Earth is destined to lose its oceans to the rising heat of a still healthy, still middle-aged sun. We have a model for what this fate looks like, and it is sitting right next door. The planet Venus is almost exactly the same size as the Earth, made of much the same materials, formed in the same era from the same cloud of dust around the same young sun. By rights it should be a sister world to ours. Instead, it is a vision of hell. Venus suffered a runaway greenhouse long ago, partly because it orbits closer to the sun and received more heat. Today its surface is hot enough to melt lead, hidden beneath a crushing, poisonous atmosphere so thick that standing on the surface would feel like being at the bottom of a deep ocean. There is no water, there is no life. There is only a scorched, dead landscape under a sky that never clears. This distinction matters enormously, because Venus is not a different kind of planet that was always doomed. Venus is a warning. Venus is in a sense the Earth's future, the fate that awaits any world that sits too close to a sun grown too bright. As our sun brightens, the comfortable zone where liquid water can exist, the region astronomers call the habitable zone, will slowly drift outward, away from the sun. And the Earth, sitting fixed in its orbit, will be left behind, baking in a region that has become too hot, just as Venus was left behind before us. To appreciate how this truly is, consider the timeline laid against the scale of life and civilization. Complex life has existed on Earth for perhaps 600 million years. Our species, in anything like its current form, has existed for a few 100,000 years. All of written history, every empire, every war, every cathedral and symphony and scientific discovery fits within the last several thousand years. And we are told that in roughly 1 billion years the oceans will boil. 1 billion years is a span so vast that the entire history of complex life so far would have to be lived again and again, nearly twice over, before that day arrives. It is tempting to dismiss it as so distant that it has no bearing on us, but there is another way to see it, and it is far more sobering. We exist near the end of the Earth's habitable lifetime, not the beginning. The window during which a planet like ours can support complex life is not infinite, and a great deal of ours has already passed. We have arrived, as a thinking species, in the late afternoon of the living world, with the long evening already gathering at the edges of the sky. Consider what this means for any future our descendants might hope to have. A civilization that wishes to survive the brightening of its own star faces a challenge unlike any it has ever known. It cannot simply adapt, because no adaptation can save a planet whose oceans have boiled away. It cannot wait it out, because the change is permanent and worsening. It has, in the broadest terms, only two possible paths. The first is to leave, to find another world, around another star, that sits in the comfortable zone where water can be liquid, and to carry life there across the staggering gulfs of interstellar space. The second is to stay, and to intervene directly in the heavens, to engineer the very orbit of the Earth, nudging it slowly outward over millions of years to keep pace with the retreating habitable zone, or to somehow dim the incoming sunlight, holding back the heat of a star that has grown too generous. Both paths require capabilities almost unimaginably beyond anything we possess today. Both require a continuity of purpose, sustained across spans of time longer than our species has yet existed. And both rest on a single quiet assumption that there will be someone left to attempt them, that the thread of intelligence and intention will hold unbroken across the abyss of deep time. Whether that thread holds is not a question physics can answer. The brightening of the sun teaches us something that is difficult to hold in the mind, because it runs against every comfortable instinct we have about the permanence of the world. The sun that feels eternal is changing. The earth that feels like a fixed and stable home is a temporary haven, granted to us for a span that is enormous by the measure of a human life, and yet strictly finite by the measure of the cosmos. The oceans will not always be here. The forests will not always be here. The gentle, breathable, water-rich world that produced us and sustains us is a passing phase in the life of a planet orbiting a slowly heating star. None of this requires the sun to die. It requires only the sun to live, exactly as it is living now, brightening by an amount too small to see in 1,000 human lifetimes, yet certain, across the long reach of the future, to remake the Earth into a world we would not recognize and could not survive. And all of this, the suffocation of the plants, the boiling of the seas, the slow transformation of a living world into a second Venus, is merely the prelude. It is what happens while the sun is still healthy. The true transformation of the sun, the part that earns the word death, has not yet begun. Now we come to the great turning point, the moment when the slow brightening gives way to violent transformation, when the sun stops being the star we have always known and begins to become something else entirely. For roughly 5 billion years from now, the sun will continue much as it has, fusing hydrogen in its core, brightening gradually, sterilizing the Earth along the way. But that long stable phase is not endless, and its ending is sharp. There comes a moment when the hydrogen at the very center of the core is finally, completely exhausted. The fuel that has powered the sun for some 10 billion years runs out at the heart of the star, and when it does, the delicate balance that has held the sun steady across all that time breaks, and the consequences unfold with a swiftness that, by cosmic standards, is almost sudden. Consider what happens at that moment. The core, now made of pure helium ash with no hydrogen left to fuse, falls silent. The fire at the center goes out, and with no energy being released, there is nothing to push back against gravity. The eternal war tips decisively to one side. Gravity, patient and relentless, finally begins to win. The helium core, unable to support its own weight, starts to contract, squeezing itself smaller and hotter. But here is the surprising part, the part that overturns every intuition about a dying star. As the core contracts and heats, it dumps enormous amounts of heat into the layer of hydrogen surrounding it, the hydrogen that was never hot enough to fuse before. Now, heated by the collapsing core beneath it, that shell of hydrogen ignites. Fusion begins again, not at the center, but in a shell wrapped around the dead core, like a ring of fire surrounding a cold stone. And this shell fusion is far more intense than the gentle core fusion that preceded it. The sun, in dying at its center, begins to burn more fiercely than ever in the layer just outside. This is the moment the sun begins to swell, and the transformation that follows is staggering in its scale. The fierce energy from the burning hydrogen shell pours outward into the vast envelope of gas above it, and that envelope responds by expanding. The sun begins to grow, not by a little, not by half again its size. it begins a process of expansion that will eventually make it hundreds of times larger than it is today. The Sun becomes a red giant, one of the most dramatic objects in the universe, an immense bloated sphere of relatively cool gas, glowing red because its enormous surface area radiates its heat across so vast an expanse that the surface temperature actually drops, even as the total output of light becomes thousands of times greater than the Sun produces now. The color red, here, is not the red of heat but the red of cooling, the same way a dying ember glows red rather than the white or blue of the hottest flame. The Sun will be brighter than ever, and at the same time, at its surface, cooler than ever. Not because it is fading, but because it has spread its tremendous energy across a surface grown beyond all recognition. To understand the scale of this swelling, you have to picture it from the surface of the Earth, if there were anyone left to watch. Today the Sun appears as a small bright disk, about half a degree across, a coin held at arm's length. As the Sun expands into a red giant, that disk will grow until it fills a vast swath of the sky, an enormous dull red dome of fire spanning a huge portion of the heavens. No longer a distant object, but a presence that dominates everything. A wall of sullen crimson light. The Sun's radius will swell to perhaps 200 times its current size, and at the peak of this phase, by some estimates, it may grow even larger, reaching out across space toward the inner planets. And as it expands, it will reach them. Mercury, the innermost planet, small and swift and close, will be engulfed first, swallowed entirely into the body of the swelling Sun, its rock and metal vaporized and absorbed without trace. Venus, the Earth's scorched twin, will follow, sinking into the red giant's outer layers and vanishing. The two innermost worlds of the solar system will simply cease to exist, consumed by the star that gave them birth. And then there is the Earth, and here the story becomes genuinely uncertain, a place where even our best calculations come to the edge of what they can confidently say. The question is whether the swelling Sun will reach the Earth's orbit, or stop just short of it. Two opposing effects are at war in the answer. On one hand, as the Sun expands, it is also losing mass, shedding its outer layers into space through a powerful stellar wind. A less massive Sun grips its planets more weakly, and so the Earth's orbit will gradually drift outward, away from the danger, as the Sun's hold loosens. This effect might carry the Earth to safety, leaving it orbiting just beyond the reach of the giant Sun's surface. On the other hand, there is a second effect that pulls in the opposite direction. The Earth, moving through the tenuous outer atmosphere of the bloated Sun and raising tides in the Sun's vast distended body, would experience a kind of drag, a slow friction that could rob it of orbital energy and cause it to spiral inward, into the very fire that the receding orbit was carrying it away from. Which effect wins is a question of fine details, and the calculations are close. Some careful studies have concluded that the inward drag wins, and that the Earth, despite its outward drifting orbit, will ultimately be captured and consumed, plunging into the red giant Sun and being vaporized along with Mercury and Venus. The honest answer is that we do not know for certain. The fate of the Earth hangs on a calculation, so finely balanced that small uncertainties tip it one way or the other. But whether the Earth is swallowed whole, or merely scorched to a barren cinder orbiting just outside the giant's surface, the outcome for the world we know is the same. There will be nothing left. The oceans will have boiled away long before. The atmosphere will be stripped. The surface, every mountain and valley and ocean basin, every fossil of every creature that ever lived, every buried trace of every civilization that ever rose, will be either melted into a glowing slag or vaporized entirely and mixed into the substance of the dying Sun. This is the devastating reality of the red giant phase. The Earth's fate is sealed not in some far cosmic catastrophe, but in the ordinary, inevitable aging of an ordinary star. There is no villain here, no disaster that might have been avoided. The same physics that makes the Sun shine and warms the Earth and made life possible is the physics that, in the fullness of time, swells the sun into a giant and erases the world. It is a death written into the laws of nature from the very beginning, latent in the sun from the moment it first ignited, waiting through billions of years of patient brightening to finally arrive. And the strangest part is how quiet it is, in cosmic terms. There is no explosion, no sudden cataclysm. There is only a star growing slowly, immensely, relentlessly larger, until the worlds that circled it are gone. But the red giant phase, for all its drama, is itself only a stage on the way to something even stranger, and at its peak, it produces one of the most extraordinary events in the entire life of the sun. An event that is violent beyond imagination, and yet so completely hidden that from the outside the sun barely flinches. Throughout the red giant phase, while the hydrogen shell burns furiously around it, the helium core has continued to contract and heat, squeezed by the ever-increasing weight pressing down upon it. And the helium in that core is being compressed into a bizarre state of matter, a state where the ordinary rules no longer apply. The electrons in the core are packed so tightly together that they begin to resist further compression through a strange quantum effect we will explore in depth shortly, a pressure that does not come from heat at all. The core becomes what physicists call degenerate, a state in which it can be squeezed and heated without expanding to relieve the pressure, the way a normal gas would. This sets the stage for a runaway. When the contracting helium core finally reaches a temperature of around 100 million degrees, something new becomes possible. The helium itself begins to fuse. 3 helium nuclei slam together to form a single nucleus of carbon, releasing energy. The dead ash that the sun produced across its entire life becomes fuel at last. But because the core is in that strange degenerate state, it cannot respond to the sudden release of energy the way a normal gas would. Normally, when fusion begins and the temperature rises, the gas expands and cools, gently throttling the reaction. But the degenerate core does not expand. The temperature climbs, and the fusion accelerates, and the rising temperature drives the fusion faster still, with nothing to hold it back. In a matter of seconds, the helium fusion explodes across the entire core in a runaway reaction of unimaginable power. For those few seconds, the core of the sun releases energy at a rate comparable to all the hundreds of billions of stars in our entire galaxy combined. It is one of the most violent events in the ordinary life of a star, and from the outside almost nothing happens. This is one of the most remarkable facts in all of stellar physics, and it deserves to be felt fully. The helium flash, as this event is called, releases a torrent of energy that for an instant rivals an entire galaxy. Yet that energy is buried so deep within the sun, beneath such an enormous overlying mass of gas, that it never reaches the surface as any dramatic outburst. It is absorbed, layer by layer, by the immense bulk of the star above it. The energy goes not into a visible flash of light, but into rearranging the core, lifting the crushing degeneracy, allowing the core at last to expand and settle into a new, calmer state of steady helium fusion. From the outside, an observer watching the sun would see, at most, a gradual change over thousands of years. The most violent event in the sun's long life happens in total silence, sealed within the heart of the star, a galaxy's worth of fury that the universe outside never sees. And when it is over, the sun has been transformed yet again. It is no longer fusing hydrogen and a shell around a dead core. It is now fusing helium into carbon at its center, burning the ash of its former life, entering a new and final chapter that will carry it, step by step, toward an ending stranger than anything that has come before. The sun that emerges from the helium flash is calmer, for a time, but it is living on borrowed and rapidly dwindling reserves. It now fuses helium into carbon at its core, in a steady, regulated way, having entered a new phase of relative stability. But this stability is brief, and the brevity itself tells us something profound about the economy of a dying star. The sun spent roughly 10 billion years fusing hydrogen. It will spend only about 100 million years fusing helium. The same star, doing what looks like the same kind of thing, burning through its fuel 100 times faster. The reason is twofold, and both reasons point in the same direction. Helium fusion releases far less energy for each unit of fuel consumed than hydrogen fusion did, so the star must burn its helium much faster to shine at all. And by this stage, the sun is enormously more luminous than it once was, pouring out energy at a tremendous rate, which means it devours its remaining fuel with corresponding speed. A star nearing its end does not fade gently into a long quiet twilight. It blazes more brightly than ever, and burns through its final reserves in a fraction of the time its youth consumed. The process by which the sun fuses helium into carbon is one of the most improbable and important reactions in all of nature, and the story of how it was understood is a small miracle of human reasoning. To make carbon, 3 helium nuclei must combine, but they cannot all 3 meet at once, for that would require a coincidence too rare to matter. Instead, 2 helium nuclei must first stick together to form a nucleus of beryllium. The trouble is that this particular form of beryllium is wildly, almost absurdly unstable. It exists for only the briefest flicker of time, a fraction of a second so small it defies any everyday comparison, before it flies apart again. For carbon to form, a 3rd helium nucleus must strike that beryllium in the impossibly brief instant before it disintegrates. By any ordinary reckoning, this should almost never happen, and the universe should contain very little carbon. Yet the universe is full of carbon. We are made of it. The contradiction was so stark that in the early 1950s, the astronomer Fred Hoyle made one of the boldest predictions in the history of science. He reasoned that carbon could only form in the necessary quantities if the carbon nucleus possessed a very specific property, a precisely tuned internal energy state that would make the final reaction enormously more likely, like a lock perfectly shaped to accept a particular key. No one had ever observed such a state. Hoyle insisted it must exist, simply because we exist and are made of carbon. He persuaded experimental physicists to look for it, and in 1957, in a laboratory, they found it, exactly where he said it would be. The reasoning had run backward, from the mere fact of our existence to a hidden property of the atomic nucleus, and the universe had confirmed it. This discovery was part of a larger revolution in our understanding, set out in a landmark scientific paper published in 1957 by Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle. That paper established, for the first time and in convincing detail, where the elements come from. Not from the beginning of the universe, mostly, but from the insides of stars. The hydrogen and most of the helium were born in the first moments of the cosmos. But nearly everything heavier, the carbon and the oxygen and the nitrogen and the iron, the very substance of planets and of living things, was forged in the nuclear furnaces at the hearts of stars, built up element by element through the kind of fusion the sun is now performing. This distinction matters enormously, because it means that stars are not merely sources of light and warmth. They are the factories of creation, the places where the simple ingredients of the early universe are assembled into the rich variety of matter that makes worlds and life possible. The carbon in your cells, the oxygen filling your lungs at this moment, the calcium in your bones, were all manufactured inside stars that lived and died long before the sun was born. As the astronomer Carl Sagan famously put it, we are made of star stuff. The atoms of your body are the recycled ash of ancient stellar deaths, and now, in the sun's helium-burning phase, our own star is adding its small contribution to that cosmic inheritance, forging fresh carbon in its heart. As the helium fusion proceeds, some of the newly made carbon captures yet another helium nucleus and becomes oxygen, the gas that fills our air and combines with hydrogen to make water. So the core of the dying sun fills, slowly, with a mixture of carbon and oxygen, the 2 elements most central to life as we know it, accumulating at the center the way the helium ash once did. And just as before, this ash cannot fuse under the conditions present in the core. Carbon and oxygen require far more extreme temperatures to fuse than helium does, temperatures the sun's core simply cannot reach. So once again the sun approaches a wall. When the helium at the center is exhausted, the core falls silent for a second time. Gravity tightens its grip once more. The carbon and oxygen core contracts and heats, and the heat ignites fresh fusion in shells around it. First a shell of helium, and outside that a shell of hydrogen. Two concentric rings of fire burning around a dead and shrinking heart. And the sun, responding to this renewed fury, swells again, even larger than during its first red giant phase, ballooning to a size and brightness that exceeds anything that came before. This final swelling carries the sun into a phase astronomers call the asymptotic giant branch, and it is the most unstable and tumultuous period of the sun's entire existence. The two burning shells do not coexist peacefully. The helium shell, in particular, burns in fits and starts, building up fuel and then igniting it in sudden bursts. Each burst sends a shudder through the star, a thermal pulse, in which the sun's output surges and then subsides, only to build toward the next pulse thousands of years later. With each convulsion, the deep currents within the sun reach down and dredge up freshly forged material from the interior, carrying carbon and other newly made elements toward the surface. And with each pulse, the sun, now grown so large and its grip on its outer layers so weak, sheds great quantities of its own substance into space. The outer envelope of the sun, the vast bloated atmosphere that once held the inner planets in its embrace, begins to lift away, blown outward by the pulses and by a powerful steady wind streaming off the star's tenuous surface. The sun is coming apart, gently, layer by layer, casting its outer self into the void. Here we arrive at one of the most important facts about the death of our particular star, the fact that determines the entire character of its ending and sets it apart from the deaths of its more massive cousins. The sun will never fuse its carbon and oxygen core. It is simply too small. To force carbon to fuse, a star's core must reach a temperature of several 100 million degrees, and to generate that temperature requires the crushing gravity of a star many times more massive than the sun. The threshold is roughly 8 times the sun's mass. A star above that limit will, after its helium runs out, go on to fuse carbon, and then the products of that, building up heavier and heavier elements in a series of ever briefer and more frantic stages. Fusing neon, then oxygen, then silicon, racing through its final fuels in years and then days, constructing layer upon layer of progressively heavier elements until it builds a core of iron. And iron is the end of the line, the element from which no further energy can be wrung by fusion. When such a massive star builds an iron core, that core collapses catastrophically in a fraction of a second, and the star detonates in a supernova, one of the most violent events in the cosmos, briefly outshining an entire galaxy and scattering the heavy elements it forged across interstellar space, seeding the gas from which new stars and planets and perhaps new life will one day form. But the sun will do none of this. The sun is not massive enough for any of it. After its helium is gone, the sun's carbon and oxygen core will simply sit there, inert, unable to fuse, while the shells around it burn through the last of the available fuel. There will be no supernova. There will be no forging of gold or uranium in the sun's heart. No violent scattering of heavy elements across space. The sun's death is a quieter affair, and in its quietness lies a kind of poignancy. The carbon and oxygen the sun has made, the elements of life it has laboured across 100 million years to forge, will mostly not be returned to the cosmos to seed new worlds. They will be locked away in the sun's dense, dead core, sealed in the stellar corpse the sun is about to become, carried into the grave rather than given to the future. Only the lighter outer layers, the hydrogen and helium of the envelope, will be cast off into space. The precious carbon and oxygen at the center will remain behind, entombed. To appreciate how this truly is, consider the strange inheritance the sun represents. Our star is itself made from the recycled remains of earlier stars that died before it was born. Stars that lived and burned and scattered their elements into the cloud of gas from which the sun and its planets eventually formed. The iron in your blood and the gold in the ground were forged in those ancestral stars and in the supernovae that ended the most massive of them, and flung outward to mix into the material that became our solar system. The sun stands in the middle of this great cosmic recycling, a recipient of the gifts of dead stars, builder of fresh elements in its own right, and yet, when its turn comes to die, the sun will give back only a portion of what it holds. It is too small to explode, too small to fuse its richest products, too small to share the carbon and oxygen at its heart. The grand cycle of stellar death and rebirth, which has enriched the cosmos for billions of years and made our own existence possible, will, in the sun's case, run only part way to completion. The sun will die having made the building blocks of life within itself, and will carry most of them, unspent and unshared, into a darkness that will last almost forever. And so we come to the final transformations, the casting off of the sun's outer self, and the revelation of what lies beneath. As the thermal pulses continue and the wind streams outward, the sun sheds more and more of its envelope, until eventually the entire outer body of the star has been blown away, expanding into space as a great shell of glowing gas. And at the center of that expanding shell, exposed at last, lies the naked core of the sun, the dense, hot, dead heart of carbon and oxygen that the star spent its whole life building toward. This exposed core is fantastically hot, hotter at its surface than the sun has ever been, and it floods the expelled gas around it with intense radiation, causing that gas to glow in luminous colors, in vast luminous rings and spheres and intricate sculpted shapes. The sun, in dying, will briefly become one of the most beautiful objects in the universe, a glowing veil of cast-off matter lit from within by the burning ember of its own corpse, a death shroud of light spreading silently outward across the dark. This glowing veil of expelled gas has a name, and the name is one of the great accidents of scientific history, a label that has nothing whatsoever to do with what the object actually is. Astronomers call it a planetary nebula. The phrase was coined in the 1780s by William Herschel, the astronomer who had discovered the planet Uranus in 1781, and who, peering through his telescope at these faint round glowing objects scattered across the sky, thought they resembled the small pale disks of the outer planets. They are not planets. They have nothing to do with planets. They are the cast-off corpses of dying stars, the blown-away outer layers of stars in exactly the situation our sun will face. But the name, born of a misunderstanding more than 2 centuries ago, has stuck, and astronomers still use it today, a small linguistic fossil preserving a long-corrected mistake. The thing the sun will become has been misnamed since before anyone understood what it truly was. To see what the sun will look like in this phase, you have only to look at the planetary nebulae scattered across our galaxy right now, the death shrouds of stars that have already passed through the stage the sun is destined for. There is the Ring Nebula, a glowing oval of coloured gas in the constellation of the Harp, looking through a telescope like a smoke ring blown across the stars, or the iris of some vast cosmic eye. There is the Helix Nebula, a great ringed structure that has earned the popular nickname the Eye of God, an enormous luminous circle with a dark centre, staring out across the void. There is the Cat's Eye Nebula, an object of bewildering complexity, with nested shells and delicate filaments and intricate sculpted forms, whose origins astronomers are still working to fully explain. When the Hubble Space Telescope, launched in 1990, turned its gaze on these objects, it revealed structures of breathtaking intricacy and beauty, glowing in luminous shades that arise as the different gases in the expelled shell are energized by the fierce radiation pouring from the exposed stellar core at the center. The shapes are not simple spheres, they are rings and hourglasses and spirals and butterflies, sculpted by the rotation of the dying star, by its magnetic fields, by the presence of companion stars, by forces that combine in ways still not entirely understood. Each one is unique. Each one is a star's individual death, made visible. This distinction matters enormously, because it overturns the gloomy picture most people carry of stellar death. We tend to imagine the death of a star as something dark, a fading and a guttering and a final extinguishing. But the death of a star like the Sun produces, for a brief time, one of the most luminous and intricate and beautiful objects the universe has to offer. The Sun's corpse will not be a dull thing. It will be a glowing sculpture of light, spreading across space, lit from within by the burning ember of the core, a structure that any astronomer on any distant world would find among the loveliest sights in their sky. The death of the Sun is not, in this phase, an absence. It is a presence, a final blaze of strange and delicate beauty, the most artful thing the Sun will ever make. And yet, for all its beauty, the planetary nebula is among the most fleeting things in all of nature, and this is the fact that gives it its poignancy. A planetary nebula does not last. The gas, flung outward at speed, continues to expand, growing ever more diffuse, spreading thinner and thinner across an ever larger volume of space. And as it spreads, it cools and dims, and the radiation from the central core, which lights it up, gradually weakens as the core itself cools. Within only 10,000 to 20,000 years, a span that is nothing at all on the cosmic clock, the planetary nebula fades and disperses entirely, the glowing shell thinning away into the darkness until it can no longer be seen. Consider what that means against the scale of the star's life. The Sun will have shone for 10 billion years. Its planetary nebula will glow for perhaps 15,000. That is a few millionths of the Sun's lifetime. If the entire life of the Sun were compressed into a single year, the planetary nebula phase would last less than a minute. The most beautiful thing the Sun will ever be is also the most temporary, a final flourish so brief that on the timescale of the cosmos it is gone almost as soon as it appears. But the gas that disperses is not wasted, and here the Sun, which seemed unable to give much back to the cosmos, makes its true contribution. The expelled outer layers, the hydrogen and helium of the envelope, along with the freshly forged carbon and other elements that the thermal pulses dredged up from the interior, do not simply vanish. They mix into the thin gas that drifts between the stars, the vast reservoir of material from which all new stars are born. The Sun's cast-off shroud enriches that reservoir, adding its substance to the great cloud of galactic gas, where it will drift for millions of years until, somewhere, somehow, gravity gathers it together with other such material, and a new star begins to form. In this way, the Sun does join the cosmic cycle of death and rebirth, not through a violent supernova, but through the gentle dispersal of its outer self into the medium that feeds new generations of stars. A part of the Sun, the lighter part, the part it could afford to give, will find its way into stars not yet born, and perhaps into worlds not yet formed, and perhaps, across spans of time we can barely imagine, into living things that will never know they carry within them atoms that once belonged to a star that long ago warmed a small blue world called Earth. To appreciate how this truly is, consider a thought that is both humbling and strangely comforting. Billions of years from now, when the Sun has become a planetary nebula, its glowing shroud spreading silently across the darkness, that nebula would be visible across enormous distances. If there were, on some planet orbiting some other star many light years away, beings who looked up at their night sky with curiosity and built instruments to study the heavens, they might see the Sun's planetary nebula glowing faintly among the stars. They would see a delicate ring of coloured light, beautiful and mysterious, and they might give it a name and study its structure and wonder about the star that made it. They would have no way of knowing that this glowing shell of gas had once been the outer body of a star that warmed a world where, long before, beings not unlike themselves had looked up at their own sky and wondered in just the same way. The Sun's death would be, to them, simply one more lovely object among the thousands of stellar corpses scattered across the galaxy, its history invisible, its story untold. And in that anonymity there is a kind of peace. The Sun will join the long roll of stars that have lived and died and given their substance back to the cosmos, indistinguishable from the rest, its particular significance to us erased by the very scale of the universe that contains it. When the nebula has dispersed and faded, when the last of the glowing gas has thinned away into the dark, the show is over. And what remains is the thing that was at the center all along, the thing the entire long death of the sun has been building toward. The exposed core, the dense dead heart of carbon and oxygen, no longer veiled by any shroud, no longer fusing anything at all, simply sitting in the dark, fantastically hot, but with no source of new energy, beginning the longest and final chapter of the sun's existence. This object is one of the strangest forms of matter in the universe, a thing so dense and so peculiar that understanding it required some of the deepest physics of the 20th century, and a battle of ideas between two brilliant men that would not be settled for decades. The sun, having shed nearly half its mass into space, having swelled and convulsed and cast off its outer self, having blazed one final time as a glowing nebula, now collapses down into a sphere about the size of the Earth, holding within that small volume close to half the mass the sun has left. Packed to a density that defies imagination, the sun has become a white dwarf. And to understand what that means and how it can possibly exist without collapsing entirely, we have to descend into the quantum world, into a strange form of pressure that has nothing to do with heat, and that holds the sun's corpse up against the crushing weight of its own gravity, through a rule that governs the behavior of the smallest particles in nature. Begin with the density, because it is almost impossible to take in, and you should sit with it for a moment before moving on. The sun's corpse will contain something close to half the mass the sun has left, perhaps a little more, compressed into a sphere roughly the size of the planet Earth. Imagine taking something as massive as a star and squeezing it down until it is no larger than the small rocky world you are standing on. The matter inside such an object is packed to a density that has no equal in ordinary experience. A single teaspoon of white dwarf material, scooped from the interior of the sun's corpse, would weigh several tons here on Earth, as much as a small truck balanced on a spoon. A sugar cube of it would outweigh a large car. The atoms inside have been crushed together until the empty space within them, the vast emptiness that makes up nearly all of ordinary matter, has been very nearly squeezed out. This is not a substance you could ever hold or touch. It is matter compressed almost to the limit of what compression can do, the densest stable form that ordinary matter can take, and the sun, in its death, will become a sphere of it. The question this raises is the deepest one in the whole story. What holds it up? The white dwarf is no longer fusing anything. There is no nuclear fire at its center generating energy, no outward push from the heat of fusion. The thing that held the sun up for 10 billion years, the pressure created by the energy of fusion fighting back against gravity, is simply gone. And yet the white dwarf does not collapse. Gravity, with all that mass packed into so small a volume, is more intense at the surface of a white dwarf than anywhere on the surface of the living sun, pulling inward with crushing force. Something must be pushing back. But there is no fire to do the pushing. The answer turned out to lie not in the physics of stars at all, but in the physics of the very small, in the strange rules that govern the behavior of electrons. Rules that had only just been discovered when astronomers first confronted the puzzle of the white dwarfs. The key is a principle discovered in 1925 by the physicist Wolfgang Pauli, a rule so fundamental that it shapes the structure of every atom and the behavior of all ordinary matter. Pauli's principle, called the exclusion principle, states that no two electrons can ever occupy exactly the same quantum state at the same time. Electrons are intensely private particles. Each one demands its own distinct state, its own particular combination of energy and motion and orientation, and no two of them will share. Under ordinary conditions, this rule is barely noticeable, because there is plenty of room and plenty of available states for all the electrons to spread out among. But inside a white dwarf, where matter is crushed to fantastic density, the situation becomes extreme. The electrons are forced together, packed tighter and tighter, and they begin to run out of low energy states to occupy. The exclusion principle forbids them from all crowding into the same low energy levels, so they are forced, against their inclination, into higher and higher energy states, which means they are forced to move faster and faster, and matter full of fast-moving particles exerts pressure. This is the strangest part, the part that overturns everything our intuition tells us about pressure and heat. The pressure that holds up a white dwarf has nothing to do with temperature. It does not come from heat. It comes purely from the exclusion principle, from the simple refusal of electrons to share their quantum states, forcing them into rapid motion no matter how cold the object becomes. This is called electron degeneracy pressure, and it is utterly unlike the pressure in an ordinary gas. An ordinary gas, if you cool it, loses pressure because its particles slow down. But a degenerate gas would maintain its pressure even if you cooled it all the way to absolute zero, the coldest temperature physically possible, because the motion of its electrons comes not from heat, but from the unbreakable rule of quantum exclusion. The white dwarf is held up not by fire, not by heat, not by any source of energy at all, but by a quantum mechanical principle, by the bare fact that electrons will not be packed into the same state. The sun's corpse stands against the crushing weight of its own gravity, on the strength of a rule about the smallest particles in nature, a rule that does not care whether the star is hot or cold, alive or dead. It is one of the most beautiful and unexpected facts in all of physics, that the structure of a dead star should rest on the same quantum principle that gives every atom its size and every element its character. The first person to apply this new understanding to the white dwarfs was a young physicist named Ralph Fowler, working at Cambridge in 1926, only a year after Pauli's principle was announced. Fowler showed that electron degeneracy pressure could indeed explain how a white dwarf supports itself, resolving what had until then been a genuine mystery, because by the older physics, a white dwarf simply should not have been able to exist. For a star mass object the size of the Earth not to collapse seemed, before the quantum era, impossible. Fowler's insight made sense of it at last. The white dwarfs were not violating the laws of physics. They were revealing a new law, written in the strange grammar of the quantum world. And we did not have to wait for the sun to die to study such an object, because there is a white dwarf almost in our cosmic backyard, orbiting the brightest star in the entire night sky. That star is Sirius, the brilliant blue-white point of light that dominates the winter sky, the dog star of ancient legend. And Sirius, it turns out, is not alone. The first hint came in 1844, when the astronomer Friedrich Bessel, working in Königsberg, noticed something peculiar about the way Sirius moved across the sky. Instead of travelling in a straight line, as a lone star should, Sirius wobbled, weaving slightly from side to side as it moved, as though some invisible companion were tugging on it, pulling it first one way and then the other. Bessel could not see this companion, but he could deduce its presence from the wobble it caused, and he concluded that Sirius must have a massive but unseen partner orbiting it. For years the companion remained invisible, a ghost detected only by its gravitational pull. Then, in 1862, the telescope maker Alvan Graham Clark, testing a fine new instrument, finally glimpsed it, a faint speck of light beside the dazzling glare of Sirius itself, the unseen companion seen at last. But the true strangeness of Sirius B, as the companion came to be called, was not revealed until 1915, when the astronomer Walter Adams, working at the Mount Wilson Observatory in California, managed to capture and analyze its light. What he found made no sense by the standards of the time. The light from Sirius B showed it to be intensely hot, a white-hot surface far hotter than the sun. And yet, despite being so hot, the companion was extraordinarily faint, giving off very little total light. There was only one way to reconcile these facts. If an object is very hot at its surface but gives off very little light overall, it must be very small, because a small surface, however hot, cannot radiate much total energy. Sirius B had to be tiny, no larger than a planet. And yet, from the way it pulled on Sirius, astronomers knew its mass was comparable to that of the entire sun, a star's worth of mass, packed into a body the size of the Earth. The density was unbelievable, beyond anything in human experience, and at first it seemed almost impossible to accept. But the light did not lie. Sirius B was real, and it was the first white dwarf that humanity came to understand. A preview, shining in our own sky right now, of what our sun will one day become. When you look at Sirius on a clear winter night, you are looking, though you cannot see it, at a glimpse of the sun's distant future. A dense and dying ember orbiting alongside a brilliant living star. The discovery of Sirius B and the others like it raised one final profound question. The question that would lead to one of the great intellectual battles of 20th century physics, and to one of its most important discoveries. Electron degeneracy pressure could hold up a white dwarf. But could it hold up any white dwarf, no matter how massive? Was there a limit to how much mass this strange quantum pressure could support? Or could you pile on more and more mass forever, and degeneracy pressure would always rise to meet it? The answer to that question would determine not only the fate of the Sun, but the fate of every star in the universe, dividing all the stars that have ever existed into two great families, those that die quietly as white dwarfs, and those that meet a far more violent end. And the answer would come from a 19-year-old student, alone on a long sea voyage, doing a calculation that his most famous mentor would refuse, for years, to believe. The student was named Subramanian Chandrasekhar, and in 1930, at the age of 19, he boarded a ship in India bound for England, where he was to study physics at Cambridge. The voyage by sea took weeks, and the young man, with little to do but think, turned his mind to the puzzle of the white dwarfs. He took the new understanding of electron degeneracy pressure and combined it with another great pillar of modern physics, Einstein's theory of relativity, and in particular with the fact that nothing can move faster than the speed of light. And when he put these two ideas together, he found something that no one had foreseen. As a white dwarf is made more and more massive, gravity squeezes it harder, and the electrons inside are forced to move faster and faster to generate the pressure that holds the star up. But there is a limit to how fast anything can move. As the electrons approach the speed of light, they can no longer speed up to provide additional pressure as readily as before. The pressure stops rising fast enough to keep pace with the ever-increasing crush of gravity. And this means that there is a maximum mass, a critical threshold beyond which electron degeneracy pressure simply cannot hold a star up, no matter what. Above that mass, gravity wins, and nothing in the quantum behavior of electrons can stop the collapse. Chandrasekhar calculated this critical mass, and the number he found has echoed through astrophysics ever since. The limit is approximately 1.4 times the mass of the Sun. A white dwarf with less mass than this can exist, stable and enduring, held up forever by degeneracy pressure. A white dwarf cannot exist with more. Pile more mass than that onto a white dwarf, and it will collapse, crushing past the point where electrons can save it, falling into something even denser and stranger. This threshold, now called the Chandrasekhar limit, is one of the most important numbers in the science of stars, because it divides the fate of every star in the universe. It determines which stars will die quietly and which will die in catastrophe, and it was discovered by a teenager on a boat, working alone, with nothing but a pencil and the deepest physics of his age. What happened next is one of the more painful episodes in the history of science, and it is worth telling, because it shows that even the greatest minds can be wrong, and that being right is not always enough to be believed. When Chandrasekhar developed and published his result in the years that followed, he ran into fierce opposition from the most eminent astrophysicist alive, Arthur Eddington, the same Eddington who had first proposed that stars are powered by the fusion of hydrogen. Eddington was a towering figure, brilliant and respected and immensely influential, and he had also been something of a mentor to the young Chandrasekhar. But Eddington could not accept the implication of Chandrasekhar's work, the idea that a sufficiently massive star, having exhausted its fuel, would be unable to stop collapsing. In 1935, at a meeting of the Royal Astronomical Society in London, With Chandrasekhar present, Eddington stood up and publicly ridiculed the younger man's result, declaring that there must surely be some law of nature to prevent a star from behaving in so absurd a fashion. It was a humiliating moment, delivered with the full weight of Eddington's enormous prestige, and it set back the acceptance of Chandrasekhar's idea for years. Much of the astronomical community, deferring to Eddington's authority, set the limit aside. But the mathematics did not care about authority. Chandrasekhar was right. The limit was real, exactly as he had calculated it, and in the decades that followed, as understanding deepened, the truth of his result became undeniable. Nearly 50 years after that meeting, in 1983, Subramanian Chandrasekhar received the Nobel Prize in Physics, and the limit that bears his name is now one of the bedrock facts of how we understand the deaths of stars. For our Sun, the Chandrasekhar limit brings reassurance in its way. The white dwarf the Sun will leave behind will contain roughly half the mass of the Sun, perhaps a little more, comfortably below the critical threshold of 1.4 solar masses. This means the Sun's corpse is safe from further collapse. Electron degeneracy pressure will hold it up not for a while, but forever, against all the patient crushing of gravity. The Sun will not collapse into something denser. It will not become one of those stranger, more violent stellar corpses that await the heaviest stars, the neutron stars in which an entire star's mass is packed into a sphere the size of a city, or the black holes in which gravity wins so completely that not even light can escape. Those terrible fates are reserved for stars far more massive than ours, stars whose cores exceed the Chandrasekhar limit and which therefore cannot be saved by the pressure of electrons. The Sun is a modest star, and it will have a modest death. It will become a stable white dwarf, and it will remain a white dwarf, held up by quantum pressure, enduring quietly in the dark. In the great division of stellar fates, the Sun falls on the gentle side of the line. And so we come to the final chapter, the longest chapter of all, longer than everything that came before it combined, longer almost beyond the power of the mind to grasp. The white dwarf, the Sun's corpse, has no source of new energy. It is not fusing anything. It shines, when it first forms, only because it is still fantastically hot, holding the leftover heat of its long and violent formation, with a surface temperature that can exceed 100,000 degrees, far hotter than the living Sun. But with no fire inside to replenish that heat, the white dwarf can only do one thing. It can cool. Like a poker pulled glowing from a fire and left in the cold air, the white dwarf radiates its heat away into space, slowly, steadily, with nothing to replace it. And as it cools, it dims, and it changes colour, fading over the ages from brilliant white to a softer yellow, and then to orange, and then to a deep dull red, growing fainter and darker with each passing eon, the last glow of a star sinking gradually toward darkness. Something remarkable happens deep inside the white dwarf as it cools, a transformation that gives the Sun's corpse a final, strange dignity. As the temperature falls far enough, the carbon and oxygen ions packed within the white dwarf, which have until now been jostling about freely, begin to settle into an ordered, regular arrangement, locking into a rigid structure, a crystal. The interior of the white dwarf crystallizes, from the center outward, the chaotic crushed matter of the dead star organizing itself into a vast, dense, ordered lattice. The Sun's corpse, in the slow cold of its long fading, will quite literally turn to crystal, an immense crystalline sphere of carbon and oxygen, drifting silent and dark through space. There is something fitting in this, that the star which gave so much warmth and light should end as a single great cold crystal, the most ordered and structured form its matter could possibly take, a final stillness after billions of years of fury. But here is the fact that may be the most staggering of all, the fact that places the death of the Sun against the true scale of cosmic time, and reveals how young, how impossibly young, our universe still is. The white dwarf cools, yes. In theory, given enough time, it would radiate away all its heat, cool all the way down, and become a cold, dark, dead object emitting no light at all, a black dwarf, the final and ultimate end state of a star like the Sun. But the cooling is so extraordinarily slow that this end state has never been reached anywhere in the cosmos. Not once. Not by any star. The time required for a white dwarf to cool completely into a black dwarf is estimated to be something like a quadrillion years, a number with 15 zeros, vastly longer than the entire age of the universe. The universe, as best we can measure, is about 13.8 billion years old. The time needed to make a single black dwarf is roughly 100,000 times longer than the universe has so far existed. This means that no black dwarf exists anywhere. The universe is far too young to have produced even one. Every white dwarf that has ever formed, including those that formed when the galaxy was young, billions of years ago, is still cooling, still faintly glowing, still warm by the standards of that immense future. The Sun's final, ultimate form, the cold dark crystal at the absolute end of its story, will not come into being until the universe is unimaginably older than it is today, in an era so distant that everything we know, every star now shining, every galaxy now turning, will have long since faded into history. To appreciate how this truly is, hold these two timescales side by side. The Sun has lived for 4.5 billion years, and will live, in its current form, for perhaps 5 billion more. Its red giant phase, its planetary nebula, its dramatic transformations, all of that will be over within a few billion years after that. A long time, but a comprehensible one. And then the white dwarf will simply persist. It will cool and crystallize and fade across a span of time so vast that the entire age of the universe up to this moment is the merest sliver of it. The Sun's corpse will still be there, drifting through the dark, long after the last bright stars have burned out, long after star formation itself has ended for lack of fresh gas, long after the galaxies have grown dark and cold. In a strange and unsettling sense, the Sun is nearly immortal in its death. The living, shining, warming Sun is the brief and passing phase. The cold, dark ember it becomes is the part that endures, the part that will outlast almost everything, persisting in silence and darkness for a span beside which the entire history of life, of the Earth, of the shining Sun itself, is nothing more than a single bright morning before an evening that never ends. This, then, is the true and complete answer to the question of what will happen when the Sun dies. It will not explode. It will not simply burn out and vanish. It will swell into a red giant and consume the inner planets, and very likely the Earth as well. It will convulse and shed its outer layers and blaze for a cosmic instant as a glowing nebula of breathtaking beauty, and then it will collapse into a white dwarf, a sphere of impossibly dense matter the size of the Earth, held up against its own gravity by a quantum rule about electrons. And it will cool and crystallize and fade across a span of time so long that the universe is not yet old enough for the final darkness to have arrived. The Sun's death is not a single event but a transformation, not an ending but a slow becoming, and what it becomes, at the very last, is a cold, dark, silent crystal, drifting forever through a universe grown old. That is the fate of our star, and it raises, inevitably, the question that no equation can answer, the question of what all of this means for us. The brief warm creatures who happened to evolve on a small world during the narrow window when this particular star was shining, and who are able, alone among everything the Sun has ever warmed, to look up and understand the story of its death. That question is older than astronomy. It is older than writing. Long before anyone understood what the Sun was, human beings looked up at it and felt something stir, a mixture of gratitude and fear and longing that has no single name. And now we know what they did not. We know that the warmth falling on our faces comes from the slow destruction of matter in a core we will never see. We know that this destruction has a beginning and a middle and an end. We know, with a confidence that would have astonished every generation before our own, roughly how the story finishes. And so the ancient feeling returns, but changed, deepened, sharpened by understanding into something the old skywatchers could never have felt. We are the first creatures in the history of life on this planet who have looked up at the sun and known that it is going to die. It is worth sitting with how strange that is. For more than 3 billion years, life existed on Earth without the faintest idea of what the sun was or where its light came from. Bacteria fed on it, plants turned their leaves toward it, animals timed their entire lives around its rising and setting. And not one of them understood that the light was the death of matter, or that the source of that light would one day swell and consume the very world it had nourished. Only in the last 100 years, the merest flicker at the end of that immense span, did a single species finally work it out. We arrived late, impossibly late, in the life story of our star. The sun is 4.5 billion years old, and human beings capable of understanding it have existed for perhaps a few thousand. If the entire life of the sun so far were compressed into a single year, all of recorded human history, every empire and cathedral and discovery, every person who ever lived and was remembered, would occupy the final few seconds before midnight on the last day. Here is the first thing the science forces us to confront, and it is not the death of the sun at all. It is the near certainty of our own absence from it. 5 billion years is not a length of time that human intuition can hold. Anatomically, modern humans have existed for roughly 300,000 years. Civilization in any form we would recognize, for roughly 10,000. The pyramids, which feel ancient almost beyond comprehension, are not yet 5,000 years old. Now set those numbers beside the 5 billion years that remain before the sun even begins its transformation into a red giant. The gap is so enormous that it breaks the mind a little to look at it directly. Whatever happens to the sun will happen on a stage so distant in time that there is almost no chance we, as we are now, will be present to witness it. This is the part that quietly rearranges everything. When most people imagine the death of the sun, they imagine it as a threat, a catastrophe bearing down on humanity, something to be feared or escaped. But the truth is gentler and stranger than that. The death of the sun is not coming for us. It is coming for whatever exists 5 billion years from now, and whatever that is, it will not be us. It may not be human in any sense we would understand. The span between now and then is longer than the span between the first complex animals and ourselves, many times over. If our descendants survive that unimaginable stretch of time, they will have changed beyond all recognition, shaped by forces and choices we cannot begin to predict. And if they do not survive, then there will be no one to mourn the sun at all, no one to stand on any world and watch it swell and redden, no eyes left anywhere that remember what it once was to us. So the real question, the one that actually has weight for a living person today, is not whether we will be there at the end. We will almost certainly not be. The question is what it means to know, right now, in this brief warm moment, that the end exists at all. That is the knowledge no generation before ours could carry, and it is knowledge that can be held in more than one way, that can settle into the human heart along very different paths, and it is worth walking down each of them honestly before we reach the end. Perhaps this knowledge is simply and purely sad. There is a case to be made for grief, and it is not a weak one. Everything that life on Earth has ever produced exists because of this star. Every forest that ever grew, every creature that ever drew breath, every human face that ever turned upward in wonder or fear, all of it was paid for in the slow currency of the sun's destruction, and all of it sits on a world that the sun will one day render uninhabitable and very likely swallow whole. The cave paintings and the symphonies, the languages and the love stories, the patient accumulated knowledge of 10,000 years of civilization, the laughter of a child who lived and died without ever once thinking about astronomy. Every trace of every life lived under this light will be erased by the very thing that made it possible. There is no monument that survives a red giant. There is no archive the white dwarf preserves. From a certain angle, The whole of earthly existence looks like a candle lit briefly in a warm room, knowing the room itself will one day be consumed by the flame that lit the candle. To feel sorrow at that is not foolish. It is one of the most human responses there is. Or perhaps this knowledge is something else entirely. Perhaps it is not sorrow that the science should leave us with, but a strange and unexpected peace. Consider what the death of the sun actually is, stripped of our fear of it. It is not a punishment. It is not a failure. It is not the universe singling out the earth for destruction or turning against the life it produced. It is the most ordinary thing imaginable. Every star that has ever existed has died this way, or in some related way. The atoms that make the sun were themselves forged in the deaths of older stars, scattered across space, gathered again by gravity into the cloud that became our solar system. The carbon in every cell of your body, the oxygen in every breath you take, the iron in your blood, all of it was manufactured inside stars that lived and died before the sun was born. We are not separate from this process of stellar death. We are made of its leftovers. We are, quite literally, what happens to the ashes. Seen that way, the death of the sun is not an ending imposed on us from outside. It is the next verse of a song that has been playing since the universe was young, a song we are not merely listening to, but are made of. The sun will return its substance to the galaxy, just as older stars returned their substance to make the sun. Some of that scattered material may one day gather into new stars, new worlds, perhaps even new life, enriched by the very carbon and oxygen the sun spent its existence creating. The death of our star is not the closing of a door, it is the opening of another, and there is a quiet dignity in belonging to something that old and that vast, in being a brief arrangement of borrowed atoms that will in time be returned and used again. Not lost, not wasted, returned. Both of these responses are true at once, and the science does not tell us which to feel. It cannot. The facts are the same whether we meet them with grief or with peace, and the universe is supremely indifferent to which we choose. That indifference is worth understanding clearly, because it sits at the heart of everything this story has to teach. To grasp it fully, it helps to step back one final time, further than we have stepped before, and place the death of the sun against the longest timeline there is, the life story not of a star, but of the cosmos itself. We live in what astronomers sometimes call the stelliferous era, the age of stars. It is the time when the universe is full of light, when galaxies blaze with hundreds of billions of suns, when new stars are constantly being born from clouds of gas while old ones die. It feels permanent. It feels like simply the way things are. But it is not permanent, and it is not even particularly long, measured against what comes after. The age of stars is a chapter, and like every chapter it will end. The universe is roughly 14 billion years old now. The age of stars will last, by current estimates, for something like 100 trillion years before the gas runs low and the last new stars flicker into being. That sounds endless. It is not. It is merely the beginning. To feel the scale of what follows, you have to let go of every familiar unit of time. After the last stars form, they will live out their lives and die, the smallest and dimmest of them lingering for trillions of years, far longer than the bright stars like the sun. Eventually, though, even the longest-lived stars will fade. The galaxies will grow dark. Star formation will end forever, because the raw material will have been used up, and the universe will enter what theorists call the degenerate era, a vast stretch of time populated not by shining stars but by their corpses. White dwarfs slowly cooling into black dwarfs, neutron stars spinning down, and the dim cinders of failed stars drifting in the dark. This is the era our sun will belong to, a cold crystalline ember among countless others, in a galaxy where nothing shines anymore. And this era does not last for billions of years. It lasts, according to the best current models, for something on the order of 10 to the 30th or 40th power of years, a number so large that writing it out would mean a 1 followed by 30 or 40 zeros. Even that is not the end, if the deepest theories are correct, and here honesty demands that we slow down and admit how uncertain this all becomes. Much of what physicists say about the truly distant future is theoretical, built from our best current understanding but reaching so far beyond anything we could ever observe that it must be held loosely. With that caution firmly in place, the models suggest that even the stellar corpses are not truly permanent. If protons themselves slowly decay, as some theories predict, then over spans of time approaching 10 to the 40th power of years and beyond, even the white dwarfs and neutron stars would gradually evaporate, dissolving atom by atom into faint radiation. What would remain afterward would be the black holes, and the universe would enter the black hole era, an almost inconceivable stretch in which these dark objects would be the only significant structures left. And even they would not last forever. Through a slow quantum process first described by the physicist Stephen Hawking in 1974, black holes themselves slowly leak energy and shrink, and over time spans best written as 10 to the 100th power of years, a 1 followed by 100 zeros. Even the largest black holes would finally evaporate into nothing, and then, at the very end of all things, the universe would enter what is sometimes called the dark era. No stars, no corpses of stars, no black holes, only a thin, ever-thinning haze of stray particles and faint radiation, spreading out across a space that continues to expand and cool, drifting toward a state physicists call heat death, a condition of maximum disorder in which everything is the same temperature, nothing is hotter than anything else, and no further change is possible, because there is no longer any difference anywhere to drive it. It would be the quietest state the universe could reach. Not violent, not dramatic, simply uniform, and cold, and still, forever. This is one possible ending for everything that exists, and our sun, our brilliant, life-giving, world-warming sun, would be one of the countless small participants in that immense and silent winding down, its atoms scattered, its light long since faded, its memory held by no one. That is the full backdrop against which a single human life unfolds. You exist in a universe that stretches at least 93 billion light-years across in the part we can see, containing hundreds of billions of galaxies, each holding hundreds of billions of stars. You exist in the brief bright chapter when those stars are still burning, a chapter that will be followed by spans of darkness so long that the entire age of stars, including every moment of your life and the life of the sun, is less than the first faint syllable of an almost endless sentence. The sun's death, which seemed so vast and final when we began, turns out to be a small and early event in a story whose true length the human mind cannot hold. And in the face of all that, the universe asks nothing of you, demands nothing, expects nothing. It does not know you are here, and this is the precise point where the science hands the question back to you, because it has taken us as far as it can go. Physics can tell you how the sun will die, it can trace the fusion in the core, the swelling into a red giant, the casting off of the outer layers, the slow cooling of the white dwarf across spans of time that dwarf the age of the universe. It can sketch the long winding down of the cosmos itself, but it cannot tell you what any of it means, or how you ought to feel about living briefly beneath a star that will one day be gone. Those questions have no universal answer. They never did. Different people, standing under the same sun and holding the same facts, will arrive at entirely different places, and there is no instrument anywhere that can measure which of them is right. Some will find in all of this a reason for despair, and that is a response the universe permits. If everything ends, if even the stars and their corpses and the black holes themselves dissolve at last into cold and formless quiet, then perhaps nothing we do can finally matter, and the only honest response is to grieve. Others will find in exactly the same facts a reason for the opposite feeling, a fierce and grateful tenderness toward everything that exists right now, precisely because it will not last. If the warmth is temporary, then the warmth is precious. If the light is borrowed, then the light is a gift. The same cold truth that crushes one person lifts another, and both are standing on the same ground, looking up at the same star, reasoning from the same facts. The universe does not settle the argument. It leaves the argument to us. What the universe offers instead is something subtler than an answer, and in the end perhaps more valuable. It offers perspective, the rarest and hardest of all the things a mind can hold. To understand the death of the sun is to be forced, gently and irreversibly, into a truer sense of your own size. You are very small. Your life is very short. The span you occupy between birth and death is a flicker so brief that measured against the life of the sun, let alone the life of the cosmos, it scarcely registers as having happened at all. There is no way to learn this story honestly and come away feeling large. But here is the strange gift hidden inside that smallness, the thing the old skywatchers reached for and never quite grasped. Feeling small in the face of something vast is not the same as feeling worthless. It is, when you let it settle fully, one of the most freeing sensations a human being can know. Consider what the indifference of the universe actually means, because we tend to hear the word as an insult and it is nothing of the kind. The universe is indifferent to you. It does not know you are here. It has no plan for you, no opinion of you, no awareness of your existence at all. The sun did not begin shining in order to warm your particular face, and it will not stop shining as a judgment upon you. To a frightened mind, this sounds like abandonment. But indifference is not cruelty. The same indifference that means the universe will not save you also means the universe is not against you. It is not watching you fail. It is not keeping a record of your mistakes. It is not waiting to punish you. It simply, vastly, magnificently does not mind. And within that enormous neutrality, that complete absence of cosmic judgment, there opens up a space of startling freedom. If the universe assigns no meaning, then meaning is not something handed down to you from above, fixed and unchangeable. It is something you are free to make, here, in the warmth, while the warmth lasts. This is the quiet reversal that the whole long story has been building toward, and it is worth saying plainly. The death of the sun is not the most remarkable thing in this story. Stars die constantly. Across the observable universe, somewhere, a star ends roughly every second, and the cosmos takes no notice of any of them. The death of a star is the most ordinary event there is. What is genuinely remarkable, what may be close to unique in all the vast dark reaches we have been describing, is not that the sun will die. It is that the sun produced, on one small world, during one narrow window of its long life, a kind of matter that could look up and understand that it would. Think about what that actually required. The sun forged carbon and oxygen in the fusion of older stars and in the slow work of its own kind. Those atoms drifted and gathered, and over billions of years arranged themselves into ever more intricate patterns, until at last some of them formed brains capable of asking where they came from. The star made the stuff of which you are built, and then that stuff, after an immensity of time, woke up and turned to look back at the star that made it. For a brief moment in an indifferent cosmos, a small portion of the universe became able to comprehend itself. That is not nothing. That is, as far as we know, almost everything. In all the hundreds of billions of galaxies, across all the spans of time we have tried tonight to imagine, we have found no evidence yet of anything else that does what you are doing in this very moment, lying still in the dark, holding in your mind the entire life and death of a star. The cosmos is mostly silence and emptiness and matter that does not know it exists. You are the part that knows. You are the universe grown briefly aware of itself. The cold and ancient process of stellar death somehow folded, just here, just now, into something warm enough and complex enough to find it beautiful. The sun will not remember you. But for the length of a human life, you can remember the sun, and understand it, and feel something toward it that the sun itself can never feel toward anything. That capacity, that brief flowering of awareness in the middle of an indifferent vastness, is the strangest and most precious thing this story contains. So perhaps the right response to the death of the sun is neither grief nor fear, but attention. The sun is shining right now, not in 5 billion years, not at the distant end of the age of stars, but now, this morning, this evening, pouring out across 93 million miles of empty space, the energy of 4 million tons of itself destroyed every second, so that you can be warm, so that the world can be green, so that there can be anything here at all that is capable of noticing. Every sunrise you have ever ignored was the visible face of a process billions of years old and billions of years from its end. Every ordinary afternoon of ordinary light was a moment drawn from the narrow, precious window in which this star and this world and creatures like you happen to overlap. We spend that window almost entirely without looking. We let the light fall on us and think nothing of it. And there is no shame in that, because no one can hold the full weight of the cosmos at every moment and still live an ordinary life. But on some quiet night, perhaps tonight, it is worth remembering, just for a moment, what the warmth actually is, and how rare it is, and how briefly, in the long life of a dying star, we are here to feel it. And there is more we can do with that window than simply notice it, though noticing is where everything begins. We can fill it. The brief overlap between a warm star and the creatures it made is not only a thing to observe, but a thing to use, and human beings have always sensed this without ever quite saying it aloud. We build, knowing that the buildings will not last. We plant trees in whose shade we will never sit. We write things down and hand them to children who hand them to children of their own, carrying forward across the generations a chain of understanding that no single short life could ever complete on its own. The very knowledge of how the sun will die is itself exactly such an inheritance, assembled slowly across centuries by people who knew they would never live to see it finished, passed from Helmholtz to Kelvin, from the Curies to Einstein, from Cecilia Payne to Hans Bethe and onward, each adding a single fragment to a picture that none of them would ever behold whole. That too is what the window is for. Not only to feel the warmth, but to do something inside it, to love other brief warm creatures while they and we are here together, to learn whatever can be learned in the small time that we are given, to add some modest thing to the long human work that will outlast us, even knowing that this work too will end when the light at last fails. None of it is permanent. None of it has to be. A thing does not need to last forever in order to have mattered while it was here, and the same is true of every person who has ever lived, and it is true of you. The universe is old, and it is getting older. The stars are burning down, slowly, one by one, toward a darkness that the deepest theories suggest will one day be complete. Our own star will swell and redden and cast off its light and cool into a silent crystal drifting through a galaxy gone dark. And the span of that cold afterward will be longer than everything that has ever lived can imagine. All of that is true, and none of it can be changed, and there is a kind of peace available in simply accepting it as the shape of things. But it is not the whole truth, and it is not the part that matters most tonight. The part that matters tonight is small.